All right, here's the next problem we're going to look at. What I have here is a forklift. It's lifting up a box. All right, and we have a lot of information. We know, so we have the two wheels. We know how far they are apart. We know where the center of mass of the forklift is. And we know where the center of mass of the box is. We're told the weight of the truck, the weight of the box. And so the forklift is sitting still. It's not rotating. It's not moving side to side, and certainly not lifting off the ground or falling through the ground. So we have no acceleration of any form here. But the box is being lifted up at currently 4 feet per second squared. If you were to look in the book, there's an assumption that the book tells you to take, and that says that the center of gravity of the forklift doesn't change with lift in position. Now, students sometimes kind of balk at that, but this is what they're trying to say. Pretend the box doesn't exist, and somebody's running the forklift, and they're moving the forklift up and down. But it's not lifting anything. There's nothing on the forks. It's just looking at this whole device, which includes the forks, as it moves up and down. They're saying, assume the center of mass of the forklift doesn't change. If you were to include the box within it, certainly stuff's changing. But the box is a separate mass. We're just looking at this whole thing by itself. So in and of itself, we're saying the forks are sufficiently light that as they go up and down, if you're just looking at this by itself, this isn't changing positions. Okay? So we'll go with that. And the problem says, determine the wheel reaction forces. All right. So we're dealing with accelerations and forces. That's pointing us to Newton's law. Our equations for that are given here. The sum of the forces equals mass times acceleration. And then we had this equation we recently devised. The sum of the moments in about some point P, put that in there, is IG alpha. That should be a plus. It looks like a cross product. RPG cross RFG, where FG is simply, again, MA. Or it can be a sum of forces that are moved to the center of mass. All right. So if you look at this here, you'll notice I just paused the video and put a plus sign in there, just corrected that. So here's the free body diagram. Very simple. We have the two wheel supports, and so there's two wheels in front and two wheels in back, okay? We can see the wheel on the one side. I've basically said I'm doing this on a per wheel basis, so I have 2NA for the two wheels in front, 2NB for the two in back. They're 10 feet apart. 4 feet off the front, we have the weight of the forklift. 5 feet in front of the front axle, we have this box, which is currently going up at 4 feet per second squared and weighs 2,000 pounds. All right. The forklift and the box, neither one is moving in the X. And that's to be expected because there's no forces in the X. So sum of forces equals 0. It's boring. It's useless. We move on. Summing the forces in the Y. Now, that's again very straightforward. 2NA through both tires in the front, 2NB in the back, minus 2,000, minus 10,000. All right. Now, here's the important point. When we look at these equations, if I do not, say, cut this off and replace this mass with a force, all right, if I'm dealing with both masses at the same time, it means for every mass I'm dealing with, I will have an MA term. Likewise down here, for every mass, I will have these terms. So we got to be careful for that. So summing forces in the Y, the forklift isn't moving, so MA, 0. Has mass, forklift has no acceleration in the Y. But on the box, that's not true. So we have 2,000 over 32.2 acceleration in the box, which is 4. So we just stick that in. So it's kind of interesting. We're kind of mixing statics and dynamics together, all within the same equation. This one's not moving. That one is. All right, now we have to take the moments. And there's room for doing this a couple of different ways. The two logical spots would be to take the moments at the center of mass of the forklift, if we did that, that would wipe out both of these terms immediately. Or we could take them here. Why would you do that? Well, if this were going to tip, this is kind of a key spot. If I take them here, it makes sense physically. It wipes out 2NA as a variable. And we're going to see some other things are wiped out as well. So let's just look at that. Summing the moments at A. Here I have 2,000, 5 feet away, perpendicular distance. That is tending to go counterclockwise. That's positive. This is wiped out because we're taking the moments there. 2NB, 10 feet away, would be going counterclockwise as well. So 2NB times 10, positive. The 10,000 pounds due to weight for the forklift, 4 feet off, and that would tend to take this thing clockwise, so that's negative. And now we have our R cross FG. Now, what is FG? Sum of all forces is equal to MA, so we're just going to put the MA terms in here. And the forklift's not moving. So this term gets wiped out anyway. We're not acting it. We put this at A, but it still got wiped out because the acceleration's 0. So that, in terms of getting rid of terms, this is working for us. And we're left with, what does this term say? So let's look. For the point we picked A, not a P. We need to have R from A to the center of mass we're dealing with, and then we put MA in here. So that's going to be going from A to the box, cross, mass times the acceleration of the box. I have that right here. So what is R from A to the box? It's we're going to go over minus 5x plus something y. I don't know what that is. And then I put in mass times acceleration for this piece. 2,000 on 32.2 MA right here for y. The acceleration's in the y, so y cross y gives 0. I don't need to know how high it is. That term's not important. So I get x cross y, that would give a z. Everything works. So if we look at this thing now, I have two forces here. So we have two equations, two unknowns. We can solve for everything. NB is 1438 pounds here on each wheel, and 4686 on each wheel over there. So that problem's all set. Next problem we're going to do. This is kind of a fun one. So what I have here, I'm going to have to just read this. So problem statement says you have a 1,000 pound acrobatic diving gorilla. It's right here. Okay, and it prepares to jump off a diving board into a pool below. Okay, so this is some kind of circus act. All right, and here's the sad news for our gorilla. Unfortunately, the pin support back here at C, the pin breaks. Oops. So this is going, and gorilla's going to go flying down into the pool along with the diving board. All right. So kind of picture you got a gorilla here, and it's kind of prances down, and it goes bam, getting set to go on the board and jump out, but it goes to kind of plant to jump, and the pin busts. All right. So the diving board is 500 pounds. We'll model the diving board as a slender, rigid rod, so it's not a diving board where it's bending a lot. Okay, so it's just a rigid rod. So 1/12 ml squared for the mass moment of inertia for that. Okay, and so what we want to find out is what is the initial angular acceleration for the diving board, and the force on the roller at B here, so this roller is pushing up, providing support, at the point this fails. So we have, here's our geometry that's relevant. We see how this force is applied at an angle. 5 feet back to the center of mass of the board. From the center of mass, 3 feet to the roller, and then 2 feet to where the pin broke. All right. And we'll note that we're taking y is positive down and x is positive to the left. So that's different. You got to watch that. All right, so our free body diagram, really straightforward. Since the pin breaks, the roller is the only thing providing any sort of support, and we have 500 pounds coming down at the center of mass, and then the gorilla had, the reason that broke is that we were applying 1,000 pounds at that angle down there. So that all still applies. All right. So we sum the forces in the x. All right, so if you look at this thing, so there's no support here, so there's nothing stopping this thing from starting to accelerate off in the x direction. All right, so we take the force in the x is 1,000 times 4/5. That'll be going out in the positive x direction. That equals mass times acceleration in the x. All set. In the y, all right, we have 1,000 times 3/5 coming down. 500 going down, which is positive here. Note we took down positive. By, the support, would be negative, equals mass times acceleration. So we've got 1, 2, 3 unknowns at this point. Next, we have to take the moment. And get two logical places. We can take it here. At G, but then this is also going to be the point of where this is wanting to tip because of that support force. So we could take it here. Taking it here would eliminate that as a variable. I choose that. And I'm doing that partially because this equation's new, so I want us to get used to using these terms. So we're going to take the moment there. So if I take the moment there, I got 1,000 pounds times 3/5 coming here. That's 8 feet out. So that's going counterclockwise. So that's positive. I have 500 pounds wanting to take this thing counterclockwise. So 500 times 3, that's positive. No more forces to consider. So now we have to deal with the other side. We only have one mass. So that makes life easy that way. So I've got, that says go, I need to have a vector r from b to g, so that'll be minus 3x. And then we have fg, which is simply referring to ma. I'm going to put mass times acceleration in here. And then we also have a term, ig alpha. All right, so if I look at where this is going, mass times acceleration is going to go in here, so I already have those two unknowns. I have the by unknown, and now I've got the alpha unknown. So if I look at this, I've got 4 unknowns in here. Means I need another equation. So we'll appeal to kinematics and study this thing in just a moment, but just to develop this equation first. So here I have, going from, on this side, I need to go from b to where center of gravity is. That's over 3x. That's positive here. And then for fg, I'm going to put in mass times acceleration. Mass is 500 over 32.2, agx and agy. All right, and then back here I have my mass moment of inertia times alpha, and we'll just assume that's counterclockwise positive. So we expect when we solve for this, this is obviously going to be going clockwise. We'll get a negative answer for that. Okay, so we're just setting ourselves up. All right. So here's where I'm saying we need one more equation. So let's go find that. So I'll leave the picture there, and let's start going for that point. All right. The acceleration at b, we'll note we can express that as the acceleration at the center plus acceleration at b relative to g. And if we do that, we can start to notice things. All right, I'm just peeling to kinematics and trying to figure out what we can observe. So let's look at that. Because of this force here, how can this thing accelerate? Okay, it's obviously has the weights coming down. So the moment that pin breaks, at B can't accelerate upwards at all. Okay, it's pressing down on this. Eventually, it can start to raise as it spins. But at the beginning, all this thing can do once that pin breaks is start accelerating along the X, because this roller provides a limitation. All right? So we know as we solve for this, AB is only along the X. All right, so if we do that, then we're going to have, here's the acceleration for G, AGX, X, AGY, Y, that's the center of mass. And then we'll have, to get to B, we're going to go alpha cross R minus omega squared X. That's what I have here. So to go from G to the acceleration at B, I got alpha cross R. Well, notice X going this way is now negative. So alpha cross minus 3X minus omega squared X. Okay, now we have to, let's talk about this. When this pin breaks, this thing is not rotating. It'll instantaneously start accelerating to give rotation, but so alpha is non-zero, but omega, the moment this breaks, is this thing rotating? Nope. It has to accelerate to start rotating. So this term at failure, just at the start, the initial condition, angular velocity is 0. So that term's gone. Well, that's neat, because let's see what we have. We know that B can only accelerate in the X initially. All right. And this term, Z cross X, is in the Y. So that tells us the acceleration of B is going to be exactly equal to the acceleration in the X, okay, at the center of mass. That makes sense. And then Y, because since it can't accelerate in the Y initially, we can solve for this, and that gives us this next needed equation. We can relate the acceleration at G in the Y with the angular acceleration. All right? That's our fourth equation. All right, just appealing to kinematics to figure out what's happening. And so once we do that, we have 4 equations and 4 unknowns. I'll let you go through the work and figure this out just to do the algebra. But alpha works out to 23.4 radians per second squared. The acceleration at G is given by this. We have X and we have Y. And the force at B, look at that. The moment this pin breaks, initially, that's supporting a lot of weight. It instantly goes to almost 0. It's really small, 9.6 pounds. Really, really small. So we're going to end this video here, and we'll talk with you more later.